when diagonal elements are different. There are also other eigenvalue inclusion theorems which are not related to circles, so-called Cassini ovals, when you basically do a diagonal scaling for the matrix in such a way. So diagonal scaling means multiplying from the left and from the right by certain diagonal matrices in such a way that we want to make our matrix more diagonally dominant. So basically to increase the diagonal elements and to reduce the sizes of the Hirschsprung circles. And then such, they are not circles but more complicated intervals, but it's more of theoretical interest. So this was the, that's the reference to the Cassini ovals. That's how they look like. Sort of, okay. Now we go to methods, and we need to cover two methods this lecture. And we organize them in the following way. So we first start from partial eigenproblem. We want to compute one eigenvector corresponding to the largest eigenvalue. And this is the simplest example of a partial eigenproblem. So and this is also the simplest example of the iterative method. So it means iterative compared to direct. Direct method computes the solution in a finite number of steps, and iterative computes up to some accuracy. And also the example of the Krylov method. So we'll talk a lot about Krylov method in the context of iterative method for solving linear systems, but this is the first example. So power method and partial eigenvalue problem, we want to compute one eigenvector, and norm of x equal to 1. That's the standard constraint. Typically, there's a 2 norm. So we can rewrite this as a fixed point iteration. How we do that? So we basically have the following form. So we can express xk plus 1 as the normalized product of a times x, or write it in terms of 2 steps. So we multiply a matrix by vector, and then we normalize it. So in this case, the eigenvalue disappears from the formulation, but if we know the eigenvector, we can easily recover the eigenvector from this formula, eigenvalue. This is also called Rayleigh quotient. This is called Rayleigh quotient, ax times x. It's very important in many cases, but for now, for the power method, it's not so important. So the power method is just multiply and normalize. So we can only store one vector. So this is also an example of a one-step method. At each step, we only store one vector. And you can use it for very large matrices where the matrix by vector product is available. If the matrix by vector product is available, we do not need to have access to the elements of A. So this is the example of an iterative method, which uses only the matrix by vector product. We do not know anything about the matrix, but if we know how to multiply matrix by vector, we can check whether our vector is indeed an eigenvector. We multiply and compute the angle between Ax and x. And this is fun. So where it converges? So it converges, under some assumptions, which we'll discuss in a second, to the eigenvalue corresponding to the largest, to the eigenvector corresponding to the largest in absolute value, eigenvalue of the matrix. So, and it is needed that this eigenvalue is simple. So its algebraic multiplicity is 1, and the ratio between the second largest and the first largest is strictly less than 1. Under this condition, starting from almost every point, you are guaranteed to converge. By the way, what's the condition of the initial point in order for power method to converge? So when it will not converge to the largest, for example. Yeah, if you implement a method for a very large matrix, first you test it on a 2x2 matrix. So for example, example, consider the following matrix. So when this is A, and then the capitation xk plus 1 equals AXK, xk plus 1 equals xk plus 1 divided by the number of xk. Then you find x0 such that xk converges not to, so the largest is 1, 0, right? So x1 equals 1, 0, number 1 equals 2. But can we find starting point when it will converge to another?
0 vector?
0 vector is not allowed. x0 is not 0. We start from x0 from 1. Any other ideas?
0, 1.
0, 1. What's so special about this vector?
It's orthogonal to...
It's orthogonal, right? So if you have the starting vector that is orthogonal to our eigenvector that we are looking for, then in exact arithmetic we will always stay in the subspace that is orthogonal to this eigenvector. Right? Because in the subspace of eigenvectors, the matrix lacks like this diagonal matrix, and if you have 0 component, it will be 0. But what happens in the finite precision? If you have finite precision, you will get not 0 there even after the first step, but maybe 10 to minus something, and this would be an unstable point. Eventually, we'll get out of this so-called saddle point. So when we are talking about floating point, we may say that it will always converge to the largest. So the set of vectors that are orthogonal to the first eigenvectors is the set of measure 0 in the set of for the probability that we fall there is 0, and moreover then we have, this is the case where floating point errors will be working not for bad but for good. So they will kick us out of a bad subspace. Small perturbations will help us. Yeah, and the convergence analysis for symmetric positive definite case. For non-symmetric case, the convergence analysis is more complicated, but for symmetric it's quite, well, it's not so much different actually, but if sorry. Because we only need, since if you have symmetric Hermitian case. If you have Hermitian, then this matrix can be unitary diagonalized by unitary transformation. By unitary transformation, it doesn't change the norm, and we only need to prove this fact when A is the diagonal. So if you know how to prove this fact that A is the diagonal, then we are done. Okay, here is in the general form. So basically, we express our initial point as a linear combination of the eigenvectors of A. And then what we have, we just need to take the kth power of the corresponding eigenvector. And what we have is this is the largest one. This one becomes the main asymptotic. So that's the easy part, and this converges to basically to all the other components will converge to 0. And the convergence will be geometric, and the ratio will be proportional. That will be important later on in the next lectures. But what we need to remember about the power method, if there is a gap between the first eigenvector and the second one, we can converge quite well. For example, the largest eigenvector is 1, the second is 1/2. So you will get convergence that is 2 to the power minus k, which is normal, which is not so bad. But if it's 1, 0, 999, the convergence can be very slow. And moreover, if they are orthogonal, the convergence will be very slow. So, but still it's quite often used, although the convergence can be slow, it's often used when you only need a rough estimate. If you only need a rough estimate of the largest eigenvalue, running a few iterations of the power method will give you up to a factor 5-6 estimate. And this is used, for example, if you want to do spectral normalization in deep neural networks. When you need to estimate the largest single value, which is estimated in a similar way, You run 5, 6, 10 iterations of the power method, and you get it of order 1,000 or of order 10,000. And you do not need to have a very accurate estimate, but you have sort of order of magnitude. So power method, the main usage is to get a rough estimate of the largest eigenvalue, a rough estimate of, for example, the spectral norm of the matrix. And it's very easy to implement, right? It's very short, like 2 lines. Well, this is the part of the story which I'm not going to tell you now. Let's start. So the solution vector is in the Krylov subspace. The Krylov subspace is defined as a linear span of x0, ax0, and so on, a to the power kx0. And we are only using the last one. And if you want to have a better method for computing to solving partial eigenvalue problem, we have to use all of this information. All vectors. In this case, you get the subspace, and you look for the solution in the subspace, and this is the starting point for the Krylov subspace method. And actually, if you think a little bit, if the only thing that you can do about with your matrix is to multiply it by vector, this is the only choice how you can construct your approximation. You just multiply matrix by vector and collect them into a large. Okay, you can multiply by different random vectors, but in fact, in terms of information theory, the most informative, if you're only given a budget of k matrix by vector product, it is better to compute the product with the same vector. It will tell you much more about the matrix than multiplying it by random vectors. Okay, so that's the summary. Only matrix by vector product. So if you have a fast matrix by vector product routine, it may come from entirely different places. It may come, for example, from, again, if you go back to deep learning, it may come from automated differentiation. That's a sort of Jacobian times vector. So you never know the full matrix, you never have seen it, you cannot have access to an element and so on, but you know how to multiply matrix by vector. Then the iterative method is what you use, and the simplest iterative method for the largest eigenvalue is the power method. But there are better methods than the power method that converges much faster than the power method in almost all the cases. But that's another story. Finally, so this was partial eigenvalue problem and the power method, and the first example of iterative method and the Krylov method. So now, to the most important part of this lecture is how to, at least, just how we solve the eigenvalue problem in practice. So if you run, what happens there? So we find eigenvalues by using the so-called Schur form or Schur decomposition. So matrix decomposition is a representation of the matrix as a product of simple matrices, and there are not too many simple classes of matrices. We have unitary matrices, we have diagonal matrices, and we have triangular matrices. So triangular matrices is the case where the determinant, well, the eigenvalues are computed quite easily, because all the eigenvalues are located on the diagonal. So if you write down the determinant of the characteristic equation of the triangle matrix, we get exactly the product of lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. So the eigenvalues of the triangle matrix are located on the diagonal. So for the triangle matrix, we do not have to do anything, we just read the diagonal. So then the idea is that is to bring our matrix to the triangle form by doing unitary similarity transformation. So suppose U is unitary, and this is our characteristic equation. So this line basically proves that the characteristic polynomial of A minus of A is the same as the characteristic polynomial of U star AU, where U is unitary. So you just put U identity here and here, you take this out, this is 1. So if you do similarity transformation, then the determinant just doesn't change. They have the same eigenvalues. Moreover, if you know eigenvectors of this guy, that's very easy to recover the eigenvectors of this guy just by transforming. So U star AU have the same characteristic polynomial and the same eigenvalues. So then the goal is to bring the matrix A to the simplest possible form. So the simplest possible form would be diagonal, but unfortunately, if you are just given a random, an arbitrary complex matrix, it is not possible to bring it to the diagonal form. But remember the previous slide. It is possible to bring this matrix into triangle form. And this is the essence of the Schur decomposition. So this is our goal. We want to find a unitary matrix such that U star AU is an upper triangle matrix. And if we just derive this equation, this is the decomposition. Represent the matrix as a product of a unitary upper triangular unitary complex point. And this is Schur decomposition. So if we can compute Schur decomposition, then we have the eigenvalues automatically. The eigenvalues are located on the diagonal of the matrix. And there is no problem with stability. Whether this is a Jordan block or whatever with algebraic geometric multiplicity, it doesn't matter. It will come as a problem when we will try to compute the eigenvectors. When we will try to compute the eigenvectors, we see that there are close eigenvalues, we will see that there are some numerical problems, but the eigenvalues can be computed in an absolutely robust and stable way. All the eigenvalues are located on the diagonal of matrix. So, and the main